Good morning all. So in previous video we have seen all the addressing modes: immediate addressing mode, register direct, register indirect, and indexed addressing mode. So in the last video we have to discuss this program. We didn't have sufficient time, so we will discuss this program which is an example for this indexed addressing mode. So as usual, before going to this program, first step is we'll read the program properly, then we'll understand it. After understanding it clearly, then we'll write the program. So first, in this program, assume that the word USA is burned into ROM locations starting at 200H and that the program is burned in ROM location starting at 0. Analyze how the program works and state where USA is stored after this program is run. So in this question he has given the ASCII characters U, S and A. These are the three ASCII characters. Okay, so these three characters are burned in a ROM location starting at 200H. That means these are present at this 200, starting from 200H, these three characters are present. Okay, so U is at 200, at the 200 location I have U ASCII character, then at 201 I have US, then at 202 I have A. So these are the locations. At 200 I have U, 201 S and 202 A, which is in ROM location, which are burned. So now these three characters I need to send. They didn't mention where I need to store them, so I can store anywhere I wanted. So in this program they have stored this U has been stored in R0, okay, R0, and this S has stored in R1 and this A has stored in R2. In these three registers I have stored U, S and A. Okay, so my program is already in RAM locations starting from 200. I have U, S and A. These are the ASCII characters. So that ASCII characters I need to move to some different registers. I have taken R0, R1 and R2 in these three registers. So I need to write a program for that. So to write a program for that, see first org 000H, that means the program where I am starting my program, okay, that I am starting at 0000H. At this address I am starting, so burn into ROM starting at 0. Next, see here move dptr comma, he has already mentioned 200 is the starting location, then 201 and 202. These are the three locations where I have these characters, because only he has given 3. If he has given 4, then 203, in 203 you will have the other value, but there is only 3 ASCII characters, that is U, S and A. So from 200, yes, before going to this we will just see this first. See, this is your program ends here. This is also part the complete program from there to here. So here first see you have org 200. That means you need to first burn that in 200 location. You need to burn these characters. You need to store those characters. Okay. So at 200, first I am starting my program at 200. There my data will be equal. So here 200. We are starting at 200 by writing org 200, and after that see here I have given my data. Okay, here db data byte. My directive is here I have written this USA, the 3 characters. So at this 200 location U will be stored, 201 S will be there, 202 A will be stored, okay, in these 3 locations. If I write this in a double quotation, it will a complete character, I can write, all the ASCII characters I can write in one statement. But if I take single quotation, I need to write each single ASCII character in each single quotation. But here they have taken double quotation where I can write all together. Yeah. So by doing this I have stored. After that I am just ending it here. Okay. Here my program will be terminated. Okay. So this is nothing but data is stored in a code space starting at 200 location. I am storing this data in some ROM location of 200. Now I am taking this data from 200 location, I am storing it into R0, R1 and R2. For that I am writing a program using this indexed addressing mode. So in this move, the program where I am writing is, this is the code, that is the code what you have written to store in ROM, and this is the code where you are writing to move that value from that 200 location into different registers. So 000H, next move dptr comma 200H. Okay. So generally you need to write 0200H. Okay, 16 bits dptr. So whenever you write that, your dptr will point towards this 200 location. Okay, when it points here, first I am clearing A. Why I need to clear A is in indexed addressing mode, I will always use, I am trying to copy the so and so contents from the code memory. So whenever I am copying, I will write move C. See here he has written move C. Then always I should move that into accumulator only. Whenever I use this statement, I can't use some R0, I can't move into some other registers, I should use only accumulator. So A comma @A plus dptr. Okay, so that means here in this statement, what I am going to say is, this A is destination register, and @A means here I already cleared A, that means A is equal to 0. So this @ here I have A plus dptr. So now this A will be equal to 0 because I already cleared A. Next dptr is pointing towards 200 location, plus dptr is equal to 200. So that will be equal to 0 plus 200, complete solution will be equal to 200. Okay, that means @ this means inside this I have, it is pointing towards 200. So inside 200 I already have U. So that U will be moved to this A. Here whatever the move C comma A I have written, in that destination this U will be moved. The ASCII character will be stored in A register after execution of this instruction. Now every time I need to move that into accumulator, right? Now in case if I try to move 201 using indirect addressing mode, if I take @, so if I try to move S, then again it will move into A, that means U will be replaced by S, sorry S will be, yeah, U will be replaced by S. So here what I have to do is, I'll try to store that value in some other register. So I am writing here move A comma R0 in this line. So whatever is there in A accumulator will move into R0. So I am trying to save A, first word is U, right? I am storing U in R0. This is done. Okay, so till here, till this line, what all I did is, I pointed my dptr to 200 location, then I cleared A, I made A is equal to 0, then by using indexed addressing mode, I tried to add this accumulator and dptr, then I tried to move U, ASCII character U into accumulator. After that, from accumulator I stored in R0. Okay. Now even though accumulator, if I make accumulator as 0 or if I make accumulator loaded with some other value, that doesn't matter to me, because U I have stored in R0 register. All I want is this. Now after that, what I need to do, I need to from 200 I have taken U. Now I should take from 201, I should take S. Okay, so for that I need to increment dptr. After incrementing, again I'll clear a. Okay, after clearing a is equal to 0 in this point. dptr now is pointing towards 2 not 1. Okay, it is pointing towards 2 not 1, and I made a is equal to 0. Now I should again write this instruction, move c a comma at the rate a plus dptr, means now in this case you see this instruction same, at the rate of ai made 0. Yeah, ai made 0 plus dptr, now it is pointing towards 2 not 1. So after addition of this, my total result will be 201. So inside 201 I have s here. So this s will be moved to this a here. Is that fine? Now after execution of this line, accumulator will be equal to s. Okay, ASCII character s will be moved into this accumulator. Now again I wanted to store that accumulator in some other register. I'll I'll take R1 and I'll store S. Okay, so I'm writing this instruction, move R1 comma A. Okay, after that again I wanted to send to take information from this 202. That means I need to increment dptr. Next again I'll make a is equal to 0. Again the same instruction. So here a will be equal to 0 and dptr will be pointing towards 202. So when I add 0 plus 202, the result will be 202. So now in 202 I have a. Okay, so I need to write this instruction, move c a comma at the rate a plus dptr. That means a, ASCII character a is moved to accumulator. So now I'll again store that a in R2 by writing an instruction, move R2 comma a. After this, see here I am writing here s jump here. So my program will be I can just terminate my program, because this is what my program is. He asked me to burn the so and so characters in the ROM location where we have already done. In a, down of that you have 4 more lines where you burnt that. Okay, so you stored that in ROM location starting from 200, that you have done. After that he asked us to move from these locations into some registers. Okay, stored in some other registers we have done using this program. So here sjump here means this line is used for termination. So it is nothing but sjump. This instruction is important here. Sjump means short jump. Okay, it will jump to certain relative address. See here, this here generally we should write the relative address. What is relative address means? Where we need to jump, we need to write that address. So I wanted to jump again here. Okay, it will jump here. When it sees this related, here instead of writing an address, I am writing here. That means I am writing some label. I am giving some label to that address. Okay. So practically when you do, you can calculate that address and you can write it. So it will jump here. Whenever I write this instruction, it will short jump. Short jump means it will just skip some amount of while learning the instructions we'll see you have L jump, S jump, okay, such instructions. So long jump means till how much how many pages it can jump. Short jump means till how many lines it can jump. It has those things, so we will see about that before. So short jump means to certain amount it jumps to certain place. After jumping there, it will check where it need to be jumped. I will write that address. So that address, it will just go and jump here, because that address is here itself, the label. Again this line will be executed because it's jumping in this line itself. So again it will see short jump, and again it will see here, again this it will jump here, then again this line will be executed. Okay, after execution of this line, what it does, again it will see this here label, again it will jump here. So this process keeps on happening. That means I am terminating my program here. Okay, because further it is not moving anywhere, it is in that line only, it is looping by itself. Okay, so after this, see I also have here I have written, see this data at 200 location I have stored this first this ASCII characters. If I store some other values, that values will be loaded into that register according to this program. Okay, so here he has written end. So here also we can write end, doesn't matter, I am ending the program here. Okay, instead of writing here as jump here, you can directly write end as well. So yeah, see the same explanation he has given here. I'll just read it for you all. In the above program, ROM locations 200H to 202H have the following contents. See, that means these contents. 200, in 200 you have U, and in 201 you have S, and in 202 you have A. These are ASCII characters. Yeah. We start with DPTR. See, ASCII character, you can write it as ASCII character, means you will just write in this way, okay, in this single inverted commas or double inverted commas. If you write it in binary, you should write a binary number and you should give B over there. If you write it in decimal, no need of writing D, because by default it will take decimal. If you write hexa, you should mention H. So same way, this whatever you write, in the end it will take it as a binary itself, machine, okay. Inside, whenever the process is going on, it will consider it as a binary itself. So for this ASCII characters, yeah, we'll see here. We where did we stop here? We, in the above program, ROM locations 200H to 202 have the following contents. In 200 you have U, in 201 you have S, in 202 you have A. So we start with DPTR is equal to 200. So first what we are doing, we are pointing DPTR towards 200. We are storing this. Next I am making A is equal to 0. Okay. See, this is what he is saying. First DPTR was made equal to 200. Then I made A is equal to 0. And after that the instruction move C A comma @ A plus DPTR moves the content of ROM location 200. Okay, that means 200 plus 0 is equal to 200 to register A. Okay, so in 200 whatever it is there, in 200 you have U here. Okay, so that will be moved into A. A is equal to U now. After that, register A contains 55H, nothing but in which line are we? Yeah, register A contains 55H, the ASCII value for U. For this U, the ASCII value is 55H in hexa. Okay, so if you convert, you will get 55H, the ASCII value for U. Next, this is moved to R0. So whatever is there in A, I am trying to move that into R0, because in this 8051 all the values are in hexa itself. It will take as a hexa and will convert it into binary, okay, internally. So 55H in R0 I have 55H, in A also I have 55H itself. If you say in terms of hexa, you can write it as 55H. If you say in terms of ASCII, you can say as U, okay, ASCII character U. So that is moved to R0. Now in R0 55 is stored. This is done. After that, next what you are doing, you are incrementing DPTR. From 200 you will move to 201 here now. You are incrementing DPTR to make DPTR equal to 201. Okay. After that, we will again make A is equal to 0. See, A is set to 0. Again to get the contents of the next ROM location 201, which holds character S. Okay. This will hold the character S. After this program is run, we have R0, after that line is been executed, which line? First we are incrementing DPTR, then we are making A is equal to 0. Again, see, this instruction will be done. This instruction will be executed. When we execute this instruction, A is equal to 0, DPTR this time will be equal to 201. So that means from 201 value will be moved into A. That means S will be moved into A. So after execution of that line, R0 will have 55 itself, but this time R1 will have 53. Okay. Now next, again what will I do is, again I will increment DPTR. Okay. After incrementing DPTR, next again I will make A is equal to 0, accumulator is equal to 0. Then again I will execute this. This time this DPTR will point towards 202. So 0 plus 202. So from 202 whatever ASCII character you have here, A will move into accumulator. So for ASCII character A, if you write it in hexa, that is 41. So from A to again you need to move to R2. Okay, so R0 has 55, R1 has 53, R2 has 41. Nothing but you can also say R0 has U, R1 has S, R2 has A, USA. These are the ASCII characters for hexadecimal values for ASCII characters. For U it is equal to 55H, for S it is equal to 53H, and for A it is equal to this 41H. Okay. So this last line he has written is, after this program is run, we have R0 is equal to 55, R1 is equal to 53 and R2 is equal to 41. The ASCII values of the characters U, S and A. Okay. So read the question properly, try to analyze what he has given and what we should do. Okay. Then we need to write the program depending on that. So this is one of the example program for indexed addressing mode. Yeah. So now we will see the bit addressing levels. So here he has mentioned the general purpose register which starts from 30H to 7FH. Okay, so that can also be called as scratch pad. So that is where is this? This is an internal RAM location. So in many applications we use RAM locations 30 to 7F as a scratch pad. We use R0 to R7 of bank 0. Yeah, this already we discussed in the previous video. It is like we bank 0. By default we take bank 0, so that is R0 to R7. Okay, that means 00 address, the address location is 00H to 07H. Next, stack pointer you will have from 08 to 1F. That is what he has given here, because by default a stack pointer it will initialize, it will be initialized at 07. Whenever you write push instruction, it will try to increment by 1 and it will start to push the values onto that stack. Next, if we need more registers, we generally go for this general purpose register. Okay, scratch pad we say. Bit addresses. Okay, generally why do we need this bit level addressing means, this also the advantages for this bit addressing. First of all, this is a faster execution of a program, less memory required by a program, program listing becomes simple and more readable. Okay, so your execution of program will be very faster. Instead of considering 8 bits, you will consider only 1 bit. Okay, so instead of going with a byte, from that 1 byte you can consider only 1 bit. You can manipulate only 1 bit, or you can execute only that 1 bit. What happens when you do only that? The time required will be reduced. So execution will be faster compared to byte addressable. Then memory also, it will take very less memory, because 1 byte means it needs 8 bits, whereas 1 bit means only 1 bit space it needs. So memory also it takes very less. Yeah, so bit addresses. Many this microprocessor allow program to access registers and IO ports in byte size only, but whereas our 8051 has a unique feature. What is that unique thing? It can have single bit operations. Single bit means we can use this set, clear, move, complement, such kinds of operations. For set you have instruction called set B. For clear you have instruction called CLR. For move you have MOV, and for complement you have CPL. Okay, these are the instructions for single bit operations, and where you can apply them. You can apply on port, memory and registers. Okay, if you come to memory, you have internal RAM memory, you have some bit addressable memory. Okay, 20 to 2FH, there you can use. And ports means all 4 ports are bit addressable as well as byte addressable. So bit addressable means for port 0 you can write each bit as P0.0, 0.1, in that way up to 0.7. Same way, same follows with port 1, port 2 and port 3. Then registers. In SFRs you have many registers. Out of those registers you can use few registers as bit addressable and few as only byte addressable. So those you can use. So see, it is a register, RAM and IO ports that need to be bit addressable, ROM holding where ROM holding the program code for execution is not bit addressable. RAM can be bit addressable, whereas ROM cannot be bit addressable. It is only byte addressable. Next, bit addressable RAM. Whatever we spoke till now, these are there here. Clearly he mentioned the bit addressable RAM locations are, see this 20H to 2FH, that is called bit addressable RAM, internal RAM. If you have any doubts, just go to the previous videos. I have discussed already about the memory organization of 8051. In that I clearly mentioned what is bit addressable, general purpose, and the bank registers memory. Okay, internal RAM is divided into 3. In that, between one is bit addressable memory, that is from 20H to 2FH. So in this 20 to 2FH, total you have 16 bytes. So this 16 bytes provide again 128 bits, because each is in that each byte has again 8 bits, right? So 16 into 8, that is equal to total 128 bits. In this location you have 16 bytes from 20 to 2FH. If you count, you will get 16 bytes. So that 16 bytes again each consists of 18. So that will be equal to total 128 bytes in this place. Okay. So generally it starts from 00H to 7FH. Okay. Clearly he mentioned in the next slides. We will see that how it is. Next, the last byte of 2FH has the bit address 78H to 7FH. Okay, we will see in that slide what it is actually. Internal RAM locations 20 to 2FH are both byte addressable and bit addressable. Okay, this bit addressable space that from 20H to 2FH, you can, if you wanted to use it as a byte addressable, even in that way you can use. Okay, but particularly for bit addressable, if you want to use, you can use this generally. Okay, it doesn't mean this is only for bit addressable, you can't use this for byte addressable. It is not like that. You can use in both the ways. Okay. Bit addressable RAM. Bit address 007F belongs to RAM byte address 20 to 2F. 80 to 7 F7 belongs to SFRs. See, from 80, okay, from 80 you have from 80 to FF you have SFRs, right? That is what is mentioning in the second point. Next, to avoid confusion regarding the addresses of 007FH, 128 bytes of RAM have the byte address of 00 to 7F, then can be accessed in byte size using various addressing modes like direct and register indirect. So in this RAM, this locations 128 bytes, we can use these two addressing modes. What are these two addressing modes? Direct addressing mode, that means you can directly use its address value, okay, like 80H, 40H, 30H, in that way. And register indirect means let it be in any register, you should first take R0 or R1. In this both you can take any one register and you should point towards that, so any so and so location. When you point by making this as indirect addressing mode, by writing a @ in front of that, you can use it as register indirect addressing mode. See, here he has given clearly how those single bits operations are. The 16 bit, this is bit addressable RAM. Under this, the 16 bytes of RAM locations 20 to 2FH have the bit addresses of 00 to 7F, nothing but 128 bits. Okay, we can use only the single bit instructions. These instructions use only direct addressing mode. Is that fine? For single bit I am talking about. I am not, see, whenever you use this place, this size, the bit addressable memory in your RAM, we can use two addressing modes. One is direct, one is register indirect addressing mode. Two we can use. But here you see this point, the instructions use only direct addressing mode. That means which instructions? The single byte instructions. That means see these instructions. Okay, if you are not using these instructions, you can also use register indirect addressing mode. Is that fine? See, now these single bit instructions are set B. Set B bit means you can write any bit. In that place of that bit, you can write P0.2. That means in port 0 your third bit will be equal to 1 in place of bit. Okay, so this bit can be anything. It can be some port, some bit of port, or some bit of accumulator. If you want to write the LSB, I mean the least significant bit of accumulator, if you want to make that as 1, you can write ACC.0. okay, this is LSB bit, right? So set B in front of this, if you write set B accumulator point ACC.0, that then you can make that least bit is equal to 1 because you are setting that bit. Okay, so in this place of this bit you can write such single bits like port 0.0 or port 2.1 or accumulator ACC.1, or if you want to make some other sorry, this is accumulator LSB. If you want to make PSW register, you have program status word. If you want to make that least significant bit as 0, or else you want to make the carry, CY carry bit is there, no, that is 7th bit. So if you want to do that, for that you can write PSW.7. okay, your carry bit will become high. So in this way you can make. Next, clear bit. See here, clear bit means instead of writing set B, I will write CLR. So when I write PSW.7th bit, the carry bit will be equal to 0 when I clear. Here also instead of writing set, I will write CLR front of this. So P 0.2 bit will become 0 instead of 1. So this is to make set and this is to make reset. So set the bit is equal to 1, clear the bit is equal to 0. Next CPL, complement the bit. Complement the bit means, see already in PS, already now we have in your accumulator, in your 8-bit accumulator, you have all ones. Okay, you have all ones, and this is your accumulator 0th bit and this is your 7th bit in this direction. Okay, LSB to MSB. So now you want to complement one bit of accumulator. You want to complement ACC.1. That means this is 0th bit and this is first bit. So instruction you will write is CPL ACC1. So then what happens is, here this bit will become, only that bit will become 0. Complement means if there is 1 it will become 0, if there is 0 it will become 1, in that way. So here you had 1 before in 0th bit and this is the first bit, here you have 1 right, so that will become 0, all will be 1s. So now by doing this, see, I am not changing the entire 8 bits. Out of this 8 bits I am changing only 1 bit, I am manipulating only 1 bit by using these instructions. Okay. So complement means if it is 0 it will become 1, if there is 1 it will become 0. So now instead of writing 1 here, if I write 7, now I want to complement 7. So now 7th bit will become 0 and this will remain 1 as it is. Only the 7th bit will become 1. Again if I execute this line 2 times, then here before first it was 1, second it became 0, again now it will become 1, all ones. Is that fine? Complement, it is just complementing from, if it has 1 it will make it as 0, if it has 0 it will make it as 1. Yeah, these are JB, JNB, JBC. So generally here you have JB means it will check for some bit. This bit can be again anything, you can write any bit, you can check for PSW bit or accumulators, any single bit, the examples we have taken here, but we will concentrate on this instruction. JB means jump if there is bit. Jump if there is bit means what does that mean is, if in that bit if you have 1, it should jump to some target, some address. Okay, you will generally write there a relative address. That address is called relative address, where you want to jump in a program. If you have written 10 lines of program, so after 10 lines if you are writing this jump bit JB and you are writing some bit in your PSW, if you have 1 in that, so please go and jump to third line, you want to write that. So here for third line you need to calculate the relative address and you need to write that. So where you want to jump, that is what target is, right? So he mentioned it as target. Okay, some label, in the way of label we can write, we have written right here is to S jump here. Same way, instead of here he has taken target, that is also one kind of label. So you write that target near that third line. Okay, so that means if there is a bit, only then it will jump to third line. If there is no bit, it will not jump anywhere. The next line of that, after that instruction will be executed. See, if you have 3 lines and in this fourth line you are writing JB some bit comma L1. L1 is your label, and if I have, see, here I am writing L1 in second line and here I have some other lines of program. So check, in this fourth line you have this instruction called jump bit. So in this bit, if this bit can be accumulators, some 7th bit or 6th bit, whatever it is, or else generally I will check for PSW register if any flag is raised or not. Okay, so if there is any carry, if there is any auxiliary carry, in that way I check. So if I want to check that bits, I can write here, or else in some ports if I want to. So if that bit is equal to 1, then it will jump to L1. That means, yeah, my programmer, this controller will go to second line, and again this second line will be executed, third line will be executed, again this jump bit, again will check for bit, if there is any bit here. If there is any set bit in that, whatever bit you have written, if there is 1, then again it will jump. If there is 1, again it will jump. It keeps on does till you have 1 in this bit. When this bit becomes 0, then it will not jump, because here the condition was given was jump if there is only bit, jump if bit. Okay, so it will only jump, but if there is no bit, it will not jump anywhere, simply it will execute the other lines. This is the other line of the program, then this, in that way. Okay, that is the meaning of that, this instruction. Now same way, this is just opposite of that. This was jump if bit, this was jump if no bit. So before, when if there was a bit, it jumped. Now if there is no bit, it will jump to the target address. And in case if there is a bit, if there is a bit means if there is high, if there is a 1 in that so and so bit, then what it does is it will simply execute the other lines, the next lines of that instruction. Okay, so if in the first instruction, if there is some bit, then only it will jump. In that bit, if there is equal to 1, only then it will jump. Here he has given clearly, jump to target if bit is equal to 1. Okay. Next, JNB means jump if no bit. So jump to target if bit is equal to 0. Jump if no bit. NB means no bit. If there is no bit means bit is equal to 0. Bit means bit is equal to 1. Okay, remember this. So if there is the bit is not equal, the bit is equal to 0, in this instruction I am talking about. If bit is equal to 0, only then it should jump to the target address. If it is equal to 1, then it will not jump anywhere. It will execute the other lines of a program. Okay, next you have JBC. Here JBC means it is same as this both, but it does one more thing. One extra feature is there in this. That is, this is same like not both actually. Wait, this is like, see this bit jump JB. Okay, but here C is added extra, means it will jump if bit is equal to 1. Okay, it will jump to the target. After jumping, here this line was ended. Okay, those lines kept on executing. But in this case, what happens is, when bit is equal to 1, it will jump to so and so target address, and it also clears that bit. Okay, if PSW dot 7, the carry bit, if you are writing JBC, here first you are writing JBC PSW dot 7 and you are writing some target address. So now this PSW dot 7 is equal to 1. What it does is, it will jump to this target address, somewhere at target address it will jump, and it will also clear this, because before it was 1, right, that it will be equal to 0 in this case. Okay, it will jump, then it will just do the so and so operations again. Wherever it jumped, from there it will do the operations, and again it will check for this if it is in a loop. Again it will check if it is 1, then again it will jump, and after jumping it will clear the bit. It will not forget that. Okay. So this is the only difference between this both jump bit and jump bit C. C means clear. Here he has jump to the target if bit is equal to 1 and clear the bit. It will also do this one more operation. It is same like this, but this operation is also been done. This bit will be cleared after jumping. Okay, again you may get doubt when it is clearing that bit, again why this bit will be equal to 1, because see, if I write this jump JBC instruction here in this line, before I will have few lines, here I will have few lines. When I have bit, it will jump to this address. I may write target address is this. Here the operations, in case if the operation is ADD, add of two numbers. Okay, when I add two numbers, those numbers can be by adding those two numbers, it can generate a carry bit again. Okay, it can make a carry bit again. So that means when it raises this carry flag, that means again this PSW.7, whatever I write here, PSW.7, again this will be equal to 1. Okay, by this operation above. So that means when this equals to 1, again the target is here, again from here it will jump to target address, and after jumping it will clear this bit, I mean carry will be equal to 0. So after going here, again it will add whatever those numbers. After adding, if it doesn't generate a carry, then it will simply follow this instructions. But if it generates a carry, it will check here. Again if it is equal to 1, again it jumps here and clear. In that way it keeps on happening in a loop. Okay. So these are the single bit instructions what you use in this for this RAM locations. See here he mentioned clearly. See in this slide there was lots of confusion. See here, this all whatever he spoke, you have to 20H to 2FH, that is bit addressable, you know till there. So in this 16 again you have 128 bytes. In that 128 bytes you have 00 to 7FH. So 0 to 7F, see 20 bit has 0 to 7. See this you remember, 20 you in this 20 to 2F, in this 20 you have 0 to 7 he said. Then in 70 in 2F, this 2F you have 7H to 7F he said. So we will see what are all those here. It is clearly mentioned. Yeah. Now see this down part here, this is bank 0, bank 1, bank 2, bank 3. Okay, the working registers of internal RAM. Then this in between this part starts from 20 to 2F. Here that is your bit addressable locations. Then the above is general purpose RAM, that is you can also call it as scratch pad. So see, we are just seeing about this because this is we already know. You have 4 banks working registers. This is general purpose or also called as scratch pad. Okay, now this is bit addressable locations. So in this bit addressable locations, it starts from 20 here, ends at 2F. That is what we know. So total you have 16 bytes. See, this is 1 byte, 2 byte, 3 byte, 4 byte, 5 byte. In that way 16 you have till here. 2F you can, if you count, you have 16. That means see in this 20 location, this is of total 8 bits. That 8 bits means one is 0, 1. See here it is there 0, 1, 2, 3. I mean location for each bit. If you write at it as 8 bit size. See, this is 0, 0 H location. Then this is 0, 1. Then this is 0, 2, 0, 3. In that way up to 0, 7. So this 20, this byte location has 8 bits, and its location, its address location is 00, 01, 02 up to 7. So this 20 is from 00 to 07H, 07H. Next 21. If you take 21 byte location, you have 08 to 0FH. In that way, same way 22 is from 10 to 17. See here it starts and here it ends. 23 has 18 to 1F. So in that way keeps on, if you keep on go 2F. 2F is from 78 to 7F. Okay, each bit address. 78 is 1 bit, 79 is 1 bit, 7A is 1 bit, 7B is 1 bit, because each byte consists of again 8 bits. We are dividing in this way because here we can this is bit addressable. I mean each bit can be manipulated individually. So I can see now if here it has a 5B. At 2B byte address, you have 5b as 1 bit. That means in 2b, if you make a 2b this complete locations, here 5b is the 0th, 1st, 2nd, 3rd. So this 4th bit of this 2b. Okay, so that bit can be individually manipulated. So this all are bit addressable. He didn't write for this above and here because they are not bit addressable. We can't see even in this bank 0, this is of one bank is of 1 byte. Okay, so when you take 1 byte, again that 1 byte has R0, R1, R2 to R7. That means R0 means 00, R1 means 01. This all are byte addresses. Okay, see this R0 again has 8 bits inside. Is that fine? But we are not mentioning R0 in bits individually because that is not bit addressable. But 20H to 2FH is bit addressable. So each bit is mentioned here individually. So we can manipulate any bit here by using these address locations. Okay. So that is what he mentioned here in this. See, here he mentioned clearly, in this 128 bytes of RAM, address of 00 to 0, not in this slide. Yeah, in this slide he mentioned. See, 20H has bit address of 00 to 07H and 2F has 78 to 7F. So in between he mentioned everything clearly in this slide. 2F has 78 to 7F. Okay. So this is about bit addressable. So here he has taken some example to make those bit addresses. So these all examples we'll see in the next video. Thank you.